Okay, I hope I'm audible. Welcome to your 7th discussion session in Mechanical Behaviour of Materials. I am Pragyandipta Mishra, a research scholar from Department of Applied Mechanics and Biomedical Engineering at IIT Madras. Today we'll be discussing about dislocation. We'll be continuing from where we left off last time. We'll be understanding how dislocation motions happens and what are the possible ways in which dislocation actually is able to move in different planes. We'll also be understanding what could cause dislocation to stop, what could cause a resistance to dislocation motion, and also understand what influences the dislocation slip or the slip behavior or plasticity in any material system. So with that out of the way, let's start our today's discussion. So let's begin with one of the dislocations, one of the two dislocations that two types of dislocation that we have studied about. Okay, so that is screw dislocation. Now in screw dislocation, there are certain features that we have learned, right? If you remember, we have talked about certain things that a screw dislocation has. First and foremost, the Burgers vector is parallel or anti-parallel, parallel or anti-parallel to dislocation line, right? Dislocation line vector. Now here Burgers vector or slip vector will always be parallel or anti-parallel to the dislocation line vector. So since they are parallel to each other, there is no unique plane which is being defined by B cross U, right? Why do you say that there is no unique plane being defined by B cross U? What is the meaning of that? It means that the Burgers vector. Okay, so what did we say in our first statement? Burgers vectors and the dislocation line vector are parallel to each other, right? So if they are parallel, if we take a cross product of two vectors which are parallel to each other, what would we get? We'll get 0, right? So since we are not getting a unique plane, we are getting a 0 as the value, we are not getting a unique plane defined by B cross U. Therefore, what will happen as a consequence of that? As a consequence of this, theoretically, infinite number of planes are available, right? Available for what? Theoretically, infinite number of planes are available for what? For slip, right? Or dislocation line motion, slip or motion. Let's not write slip so that you don't confuse yourself with slip vector. Motion. Right? So the screw dislocation can move in any direction now because there is no unique plane that is defined. So how do we know which plane will the screw dislocation move on? If we are not allowing it to move in a particular plane, let's say that there is a plane in which the screw dislocation is supposed to move. If we are not allowing it to move in that particular plane, then which direction will the screw dislocation go towards? How will we know that? So the constraints are now not defined by the screw dislocation itself, but it is defined by the slip system. So constraints for the motion are not defined by the slip system. Sorry, why did I say are not defined? Constraints are defined by the slip system. Just do this. So constraints can only be defined by the slip system. And screw dislocation by itself does not have any constraints on which direction it can move, as there is no ionic plane defined by B cross U. Okay. Therefore, a screw dislocation can move out of the plane by a mechanism known as cross slip. Okay. So this is unique to screw dislocation. Edge dislocation will not be able to do this. Why? Because it is not possible for edge dislocation to slip into another plane. Okay. So you can write that point also. Cross slip is not possible for edge dislocation. Okay. So how does this cross slip happen? So let's understand it with a schematic. Okay. So let's say we have a body like this. Okay, like we are looking at a plane for a particular body, and let's say this is the screw dislocation. The shaded part is the screw dislocation. Okay. Now let's say it's moving in this direction and it encounters some sort of resistance here. Some sort of resistance at this point AB. Okay, this place AB, it's encounters some sort of resistance. So what this dislocation can do is it can cross slip to another plane. Okay. And then continue along that plane. Okay, so it can go along this direction. And then again it can come back if required to a plane which is parallel to the initial plane. Okay, it can come back to this plane. So it goes from plane 1 to plane 2 to plane 3, which is where 3 is say parallel to 1. It can happen, it may not happen. Okay, so you might go from a plane which is parallel to, like, you might go from, like, while cross slipping, it might go back to the plane which is parallel to the original plane it was moving along, or it might not go. Okay, it might continue along the cross slip plane. It might move on to some different plane altogether. So anything can happen. Okay, but usually what happens is if the screw dislocation was moving along a very like low energy plane, and then like because of cross slip it has moved to some other plane, again it would try to go back into that low energy plane and keep moving in that direction only. Okay, it's all a matter of energy. So depending on what kind of energy the dislocation has, it'll continue moving in the same parallel plane, or it will move to a new plane. Okay, so this is known as cross slip. Okay, but here there is two cross slip happening, so we call it a double cross slip. Okay, now the same thing can we also expect in a dislocation that has mixed characteristics. So what happens? What happens to a dislocation that has mixed characteristics? So a dislocation that has mixed characteristics will have both edge and screw characters, right? But we have learned that screw dislocation will cross slip and edge does not cross slip. So here also, only the screw part of the dislocation will cross slip. Okay. So what will happen here is, say you have similarly like last time, a dislocation that was in this plane. Okay. Here if there was a dislocation which has a mixed characteristic. The Burgers vector is along this direction. So this point, the point that I've marked here, point A, is kind of having screw character, while the ends have edge characters. Okay. Now, if say this was moving along this direction, okay, and there was a something blocking it at point CD, okay, there is something that is blocking it, not allowing it to move in that direction. Then once it reaches this point, right, once it hits this point, so once it hits this CD, what will happen is the screw part will suddenly start expanding. Okay. The screw part will suddenly start expanding. This part, you can see I have shaded that part, right? And now that expanded part will start growing. Till it goes back to this original plane. Okay, it will keep growing in this direction till it goes back to the original plane. And then the other parts, the other edge character parts and mixed character parts will get regenerated here. Okay, the other part will get regenerated. So what is happening here? The screw part of the dislocation, the screw dislocation part in the mixed dislocation is actually getting stretched out to this new plane, and then the other parts of the dislocation are getting regenerated onto the new plane. Okay, so for mixed dislocation you can write down only screw dislocation cross slips while rest of the components gets regenerated onto the new plane. Okay. One important thing to note is that this particular type of motion is only possible when the intersection line, that is the line where the cross slip is happening, the line where the cross slip is happening should be along the Burgers vector, okay, which means that this line, this CD, has to be along the Burgers vector or parallel to the Burgers vector, okay. So what we can say is intersection line. Okay, here intersection line is CD. The intersection line is CD will be along the Burgers vector. So you can see here in the figure, CD is parallel to the Burgers vector. So then only this will happen. Okay, if that is not the case, if the intersection line is not along the Burgers vector, then the screw part of the thing will, the screw part of the mixed dislocation will not be able to cross slip very easily. Okay, there will be some distortion or something that will happen, and the cross slip will not happen properly. Okay. So this is one type of motion. Okay. Now there is one more type of motion that is concerned with the edge dislocation. Okay. Cross slipping, as we learned, was something to do with the screw part of the dislocation or the screw dislocation in itself, if screw dislocation is the only dislocation that is present. Now what about the edge part or edge dislocation if it is present as a single dislocation? What happens then? So there is another type of motion known as climb. Now climb dislocation is a process by which edge dislocation will move out of the plane. Okay. Okay. Just a second. So what is this climb, or what happens in this climb? Okay. So let's understand it with some figures. Okay. Let me draw it. Can I draw it here? No, I think I'll draw it in the next page. So let's say we have a crystal structure like this. Okay, 5 atoms. I'm just representing 5 atoms. Okay. Then we have one more layer. Okay. And the next layer has the dislocation. Okay, so the dislocation is somewhere here. Now what happens in climb is, so essentially there are two types of climb. Okay, so let's say the shear is being applied like this. Essentially there are two types of climb. You can either climb up or climb down. Okay, I'll write about what is climb up and what is climb down here. So in climb up, what will happen is this dislocation will try to move. So you can say that the dislocation is somewhere around here, right? Now this will try to move up. Okay, so what will happen is this atom, the atom that is present on the dislocation position, will exchange with this vacancy. Okay, so as a result, what we will see is something like this. Now the third layer is perfectly filled because the vacancy and atom exchanged. But the fourth layer onwards, now we have only 4 atoms. Earlier, from fifth layer onwards, there were 4 atoms. But now one layer, the dislocation has moved one layer up. Right? So now dislocation has moved to the fourth layer. So what we can say is, the dislocation has climbed up. It has moved up by one layer, while the vacancy has moved in. Okay? Or the dislocation is now acting as a vacancy sink. So essentially, climbing up would mean that the dislocation will move up. The H dislocation will move up, and the vacancy will fall inside the H dislocation, or the dislocation will become a sink for the vacancy. Okay. So let me write that down. Dislocation moves up. Actually, let me write H dislocation moves. So this H dislocation will move up, vacancy will move in, vacancy moves in, and dislocation will act as a vacancy sink. Okay. I hope it's clear. Just a second. Yeah, I hope it's clear what has happened here. Now there is one more type of climb known as climb down. Now what will happen in climb down? So let's draw that and find out. What will happen in climb down? Now, let's say we have vacancy and dislocation in this form. Okay, let me draw it and see. Okay, let's see. Here there are 4 atoms. in the fourth layer. Okay. So what's happening is, let's say that I moved, let's say there was, like, this is a dislocation place, right? This is the point where dislocation happens. This is a dislocation where the dislocation is present right now. Okay. So I can also say that at this place, at this point here, I also have some sort of vacancy here, right? Because one atom is missing at this place, at this point. So now instead of vacancy, so instead of now vacancy moving in, now vacancy is moving out. This vacancy is now moving up to this point. Okay, and this atom is moving here. So what will happen is, let me use a different pen. Confusing. Yeah. So okay, let's move this atom. So where the vacancy is present, now this atom is now trying to take that vacancy's place. The atom is trying to take the vacancy's place. So now what will happen is, the new structure will look something like this. So first layer as it is, second layer as it is. In the third layer, now in place of that atom, I have a vacancy. Okay, let me draw the vacancy with a different color. While in the fourth layer now, again, now I have 5 atoms. Fifth and sixth layers have 4 atoms each, like last. Okay, so now the dislocation has moved down by 1 layer, right? So it has climbed down. So essentially what is happening is, edge dislocation moves down. And vacancy moves out. So if there's a vacancy there, now it moves out of the dislocation, it goes out, right? It has gone up 1 layer. So it has gone out of the region where the dislocation is present. So vacancy moves out. Or we can say that dislocation acts as a vacancy source. That is, a new vacancy gets created from the dislocation. Okay. So this is the climb motion, right, by which edge dislocation moves out of the plane. Okay, it can climb up or climb down, depending on uh, the how the barrier is present or the resistance is present for the motion. Okay. So one important feature of climb is that it can help the dislocation to surpass any barrier that is present. Okay. So how that will happen is, climb motion Okay, so how that will happen is, let's say we have a surface like this. Okay. Now there was a barrier here. So what will happen if a dislocation is coming is that at this point the dislocation will rise up, go like this. Okay. So what you can say is now the dislocation has surpassed the barrier by climbing up. Okay. So that is how the climb will happen if this is the barrier. Okay. One important thing that also you have to remember is that climb motion is essentially dependent on vacancy, right? So since it is dependent on vacancy, vacancy diffusion will play a major role. And vacancy diffusion is all the time temperature dependent. Okay, so vacancy diffusion will generally happen at higher temperature only. So therefore, this entire climb process is dependent on temperature. It only happens at high temperature. Okay, so let's write that down. As climb involves vacancy diffusion, okay, hence it is temperature dependent. Okay, and it is active only at higher temperature. Okay, so this is something that you can remember about climb. And the barrier that we are talking about, right, is a function of the activation energy. Okay, so there is a concept known as activation energy that gives the minimum barrier for entry or the resistance for entry. So this activation energy is a vacancy diffusion value. Okay, I don't have to understand more about activation energy here at this stage, but it is enough to know that it's like an energy value that the dislocation must possess in order to circumvent that barrier using climb. Okay, so that activation energy defines how much energy is required for vacancy diffusion to happen. Okay, so essentially the motion of X dislocation can be divided into two parts, right? So it can be conservative or non-conservative. Okay. Now what is conservative? What do we mean by conservative? It means that number of sites are conserved. While non-conservative means they are not conserved. Number of sites are not conserved. Number of dislocated sites are not conserved. Okay. So conservative motion will happen through glide. That is the general motion by which the dislocation moves. Glide. While non-conservative will happen through climb. Okay. Okay. So this is about how dislocation can move out of the plane, right? Now there is some sort of resistance that is present for this dislocation to move in this way, right? So essentially this resistance will not be like a barrier that will allow dislocation to glide very easily out of the plane or like move out of the plane very nicely or cleanly, right? When dislocation is moving, it is not always such that dislocation is moving along a straight line. So all these motions that we are talking about, glide or climb or this thing cross slip, all three of them are something that we're defining when dislocation moves along a straight line. However, that is not always the case, right? Sometimes the dislocation might choose not to move in that particular in a straight line, as we have seen in the videos you would have seen, right? Sir would have shown you how in real life the dislocation will not always be in that one straight line shape, right? It will take different shapes. So if that is the case, if dislocation is not moving along a particular plane, along a particular line, then how does the dislocation actually glide? Okay. So there are two major things that you have to keep in mind when we are talking about dislocation motion. First is there is the dislocation. Okay, let me write it down. Dislocation doesn't move or down or doesn't stay. Okay, let's write. Okay, let me write it in different. Yeah. In reality, okay, dislocation don't move or don't stay as a straight line. It's not right, don't, that does not. Okay, in reality, dislocation does not stay as a straight line. So, what it does is it forms different structures known as kinks and jogs, which essentially helps it to minimize its energy while moving. Okay, so the movement becomes easier. So let's learn about kinks first. So in kinks, what is happening is, okay, what is kink first? It's a process for dislocation glide. Process of dislocation glide. Right, dislocation is still gliding. Okay. So what will happen is the dislocation will move in steps, and these steps are what we call kinks. Okay. Okay. So how will this kink look? So it will look something like this. Let's say we have a surface like this, surface where a dislocation is present, and let's say this is my dislocation, this line. Okay, so this entire thing is an edge dislocation, and it's gliding in this direction. So what will happen is, dislocation will not keep moving in a straight line. What will happen is, it will break at some place, then that part moves forward, then this part moves. So some part of it moves first, some part of it moves later. Okay, so it's something like this. Okay, so what you can see, if you divide this entire thing into regions, this is L, okay, this is M, and this is N. So these are the regions, and then again you have on the other side of N again M and L. Okay, what is happening is this region M will push itself outwards, both the sides. Okay, this will move outwards. So this N region will start growing, while the L region will shorten. Okay, it will shorten. The N region will grow, and the dislocation has now moved to the new place. Okay, that is what will happen. So this M region, this M region, let me just put it here, are the kinks. Okay. So what can we say about this L, M, and N? What kind of characteristics do these have? Now L has still an edge character, right? It is just like the edge part. L still has Burgers vector parallel to the dislocation line, right? So my Burgers vector was in this direction because it's edge. Okay. So this is still having edge characteristics. M has Burgers vector parallel to dislocation line, right? So this has screw character, while N has Burgers vector again perpendicular to dislocation line, so it also has edge character. So this is how the motion will happen through kinks. Okay. So essentially what is happening is, a small region will push itself outwards, forming a kink. Okay, and then these kinks will move across laterally, like the kink part, the M part that I am drawing, will move laterally and result in average displacement of the dislocation. Okay. Move across laterally. Okay, resulting in average displacement of dislocation. Okay. So, can we say something more about these kinks? Now, again, when we are drawing these kinks, we are drawing like very sharp kinks, right? We are drawing like a straight turn suddenly to screw, from edge to screw, and then again coming back to edge, again going back to screw, again going to edge, right? These sharp kind of corners that we are drawing, right? But the sharp corners will result in a large amount of energy being concentrated in those corners, right? And we would not want that to happen, right? When dislocation is getting formed, ideally what they were trying to do is they are trying to minimize the energy. Now if these sharp corners are getting formed again and again, and then like we are having those sharp corners, then the energy will not get minimized very easily. So in order to ensure that the energy gets minimized or the energy get reduced, the dislocation will eliminate the sharp corners by rounding it off to some extent. Okay, so let's write that down. Dislocation reduces energy by eliminating sharp corners. Okay, so roundness of the sharp corners will depend on Piles-Navarro energy values. Okay. So it will try to create this round kind of shape. Okay, this roundedness of the sharp corners will depend on something known as Piles-Navarro energy value. We'll come back. We'll come to what Piles-Navarro is in some time, but just remember this. Roundedness of the sharp corners. Will depend on Piles-Navarro energy values. Okay. So kinks are essentially what they are doing. They are creating a sharp break within the same glide plane and allowing the motion of dislocation in a much easier fashion. However, while creating that break, they do not always form sharp corners. They will try to round it off so that they can reduce the energy. Okay, so you can. So I'll come back to this. Let's go to jogs first. Actually, I'll write it down. So what are kinks? So essentially, kinks therefore kinks are sharp break within the same glide plane. It's important to understand this point, okay? Why we are saying that sharp breaks within the same glide plane? Because the next type of dislocation motion that we will discuss about will not be in the same glide plane, okay? It will be sharp break outside the plane, okay? So kings are sharp break within the same glide plane. Just remember this point, okay? So the next type of motion that we'll discuss about is jogs. Okay. So in jogs, what is happening is individual vacancies, okay, individual vacancy, any one vacancy or cluster of vacancies will like come together and it will lead to a climb. It will lead to a climb in steps. It will lead to climb in steps rather than whole row of atom uh, climbing up. Okay, so only particular part of the thing will climb up, and then that climb will be represented by this jog. Okay, so let me write that down. Individual vacancy or cluster of vacancies. Okay, individual vacancy or cluster of vacancies, they will lead to climb in steps. Just a second. Lead to climb in steps rather than whole row of atom moving. Okay. So, as we have seen from this statement, what we can immediately say is that a jog is helping you climb, right? Any dislocation climb. So it will be majorly associated with edge dislocation only because it is always helping in climb. It is not helping in like glide. It is helping in climb. So therefore we can say it is a part of edge dislocation. Okay, just a second. Some notification is coming. Okay, not important. Yeah. So let's draw this and see how this looks like. I've already drawn a climb motion, so this is exactly similar to that. Okay, so I will have one, then let's see, I have right. So this is how the jog will look like. So if I have my Burgers vector in this direction, okay, and this is my original glide plane. Okay. So because of this presence of some constraint, now a jog has been created. So I have the new disconnected portions for dislocation as L, this as M, and this is N, right? Like last time. Now I can write for L. For L, I can write the Burgers vector is perpendicular to the dislocation line, right? So L part is similar to the original dislocation where there was no change. Even the N part is the same, right? If I write about M and I write about N. N is also same as the original dislocation line. So the Burgers vector will still be perpendicular to the dislocation line. So both of them are showing H cat. Right? However, what about M? What is happening at M? Now at M, we'll see that the dislocation line has moved perpendicular to the uh, it has moved perpendicular to the original dislocation line, right? Now M is perpendicular to the original dislocation line. However, we can also see that it is still perpendicular to the Burgers vector. So we can still say it is Burgers vector is perpendicular to the new dislocation line. Let's say some U1, some new dislocation line. So it is still showing an edge character. So all of them. So in jog, you don't have edge screw edge character. You have completely edge character. Okay. So this is something that you can remember. So one important thing that you can also note down or remember is that this jog influences both positive and negative climb. Okay, so both positive and negative climb can happen through jogs. Okay, so that is also something that you can note down. Both positive and negative climbs will proceed by nucleation of unit steps. What do you mean by nucleation of unit steps? This entire process, that is jogs. Okay. So it is also important to remember that this jog is not something that happens in between, like somewhere in between or some specific place, or only one jog will be formed, right? So in reality, when you see, you'll see multiple jogs being formed, like something like this. Okay. This is how your final structure might look like. Okay. The final dislocation due to the presence of jogs. So this is how the jogs will look like in reality. Okay. And one important point to note, something that we talked about in Kings also. Kings are sharp break within the same glide plane, right? We talked about that. Jogs are sharp breaks outside the plane. Okay, so essentially jogs are like staircase. So you have sharp break outside the plane, so you can climb up or climb down the staircase. It's like a staircase. Okay. I hope everyone has understood till here what are uh, kings and jogs. Okay. Now let's move on to dislocation motion. What could be the possible resistances that could be present for dislocation motion? Okay. what could be the possible resistance to dislocation motion. Okay. Now, the resistance that is offered to dislocation motion could be coming from one of the two ways. Either it can come from the core itself. Okay, the core is not willing to move, or there is some difficulty associated with moving the core, or from the lattice. The lattice does not allow the dislocation to move. Okay, so let's study that one by one. First, let's study the core. Okay. Now, if we have two types of dislocation, okay, one where we have cores which are very widely spaced apart. Okay. Okay. So I have a big dislocation core, and one where dislocation cores are much smaller. Now this spacing could be small for any number of reasons. Okay, it could be small because the lattice size is smaller, or because the dislocation size is smaller. There could be n number of reasons why this entire dislocation core is closer or smaller. Okay. So now this is where the dislocations are. So if I am looking at this, so this was my width here. Here the width is something like this. Okay. So if I draw the displacement of this, the change in displacement, okay, if I just draw the dislocation core size with respect to each other, and then we measure how much the displacement varies with as a function of the distance from the core, we'll get something like this. For this case, we will get something like, and then from here it will be bottom, it will be like this. So similar. So this is my delta u by v, while the x-axis is just the distance. Okay. For this one, it will look like okay. So say if I want to see the distance, okay, at plus or minus 10%, because that's what people usually decide the core to be. So for this, it is cutting here, right? While for this plus or minus 10% will cut somewhere here. %10% of Burger's vector. That is what is plus or minus. Okay? Just a second. So, what we can say is that this delta u by b value at plus or minus 10% will almost die down, right? and therefore the core will offer much more resistance, okay, to dislocation motion. While if the width is larger, the dislocation core is larger, the dislocations will be easier to move. Okay. When the dislocation core is larger, when the dislocation core is larger, the dislocations are easier to move. Okay. So this width of the dislocation core is essentially the distance over which the displacement of the atoms are large enough that linear elastic theory cannot be applied. Okay. So you cannot apply linear elastic theory within this dislocation core size, meaning that everywhere else within the material system you can say that it is linearly, like the linear elastic theory is valid. Okay. So you can apply all those equations that linear elastic theory has in those other regions, but within this core region you cannot apply it. Okay. So how this dislocation core width is decided, it is usually taken as the Burgers 10% of Burgers vector, and that essentially helps us to understand where the dislocation will be easier for moving or for gliding. Okay. Now, in a similar vein, the resistance could also be due to the lattice, right? So, this lattice resistance is represented in the forms of Peirce-Nabarro energy or Peirce-Nabarro stress. Okay. So, I will not go into depth of what this Peirce-Nabarro and all that is. We'll just understand the equations associated with this Peirce-Nabarro. Okay. So, essentially, when dislocation is moving, there is a sinusoidal resistance that is present within the dislocation. Okay, when the dislocation is gliding. Now, the sinusoidal comes due to dislocation translating from one atom to other and the presence of atoms in between. Okay, so those atoms will resist dislocation motion in some form. Now, there is no need to go deeper into how that resistance is coming into play, but it is due to the lattice structure. Okay, how atoms are arranged within the lattice. It is due to that. Okay. So due to this, you have something known as Peirce-Nabarro energy, which is given by GB square. Let me just write it down. Divided by pi times 1 minus nu exponential of minus 2 pi W by B. Okay. So this is Peirce-Nabarro energy barrier due to the lattice. Okay. And since we know the energy barrier, we can also calculate the shear stress associated with it. Right. Which is equal to 2g times 1 minus nu exponential of same thing. Minus 2 pi W divided by B. So this is Peirce-Nabarro stress. Okay, how am I calculating this shear stress? We know that stress is equal to 1 by P times maximum of d by dx, not d by dx, actually del E by del x, partial derivative. Right? So using this, we can calculate this to get your Piles-Nabarro stress. Right? Now what is these terms? W, G is of course shear modulus, B is Burgers vector, mu is Poisson's ratio. What is W? Now this W is width of the dislocation core. Width of the dislocation core. Now this W is equal to, how do you find W for screw and edge dislocation? It is equal to A for screw dislocation or equal to A divided by 1 minus nu. A divided by 1 minus nu for edge. What is this A? A is interplanar spacing. Okay. Okay. So this gives you the resistance to dislocation motion by the lattice. Okay. So if we want the resistance to be lesser, right? If we want the resistance to be lesser, then A should be large, right? Interplanar spacing should be large. Therefore, you can write A should be large if we want for lower EPN, right? EPN or tau PN. A should be large. Now, this can only happen when the glide plane has wider interplanar spacing. Just a second. Glide plane with wider interplanar spacing. And it should be the densest plane. Right? Then only you'll have wider interplanar spacing, right? If it is the densest plane. Now, if you want also to increase or sorry, to lower the Piles-Nabarro energy or Piles-Nabarro stress, then you can also have smaller B, right? B should be small. So what does that mean in reality? So in reality, slip along any direction with shortest lattice translation. Okay, slip should occur along a direction with shortest lattice translation. That is, the Burgers vector should be small. Slip should occur along a direction with shortest lattice translation. And it should be along a close packed direction. So essentially, in the end, what are we trying to do? Should be on the densely packed plane, and it should be along a close packed direction. Okay. So these are the conditions for resistance to be smaller. Okay. So how do we talk about this density of plane or density or close packed direction? What do we mean by that? Essentially, there are two more terms that we have to define. Just give me a second. Sorry. Yeah. So yeah, let's coming back to the final concept for today. So how do we decide this densest plane or close packed direction? How do we decide all that? So there's something known as planar density and linear density. That is something that we have to determine in order to find which direction and which Burgers vector will this entire concept of uh, lower pulse Nabarro energy will be occurring at. Okay, so planar density is essentially atom centered on a plane divided by the area of the plane. Okay. So what do we mean by this? Means that if we want a densely packed plane, the planar density should be higher. Okay. So we should have either more number of atoms on the plane or the area of the plane should be smaller. Now what is linear density then? In that case, what is linear density? If we think along the same lines for a direction, then we will get linear density. This is just atom centered on one particular direction divided by length of direction. Okay. So this decides what is the which is the most densely populated uh, direction, and then from there we can choose the most densely populated one to be your slip direction. Okay, that is how slip direction is getting determined. Okay, so with this we can come to an end for today's. Yeah, okay. One last thing: slip systems, right? So let me just draw this table so that you can. Crystal structure, right? Slip plane, slip direction. Actually, let's keep them. Then number of non-parallel planes. And slip direction per plane. Okay. So for FCC, we have the slip plane to be 111. Slip direction to be 110. So if I'm talking about 111, this will be 1 minus 10. Okay. So number of non-parallel planes. Okay, non-parallel planes for 111 will be 4, and the number of slip direction per plane will be 3. So therefore, for this particular combination, I will have 12, 4 into 3, 12 number of slip systems. So let me just write number of slip systems here, that is 12. Okay, the one in bracket is number of slip systems, so it is 12. So number of slip systems is 12. Now for BCC, we have 3 different slip planes. Okay, so one is 110, then we have 112, then 123. Okay, So for 110 it will be 1 bar 1 1 direction. Sorry, I think here I've given the wrong bracket. Yeah, so brackets you have to be careful which brackets you are using for which case. So for 112 it will be 1 1 1 bar family of directions. For this it will be 1 1 1 bar again family of directions, right? So there will be 6 number of non-parallel planes in this case. Here it will be 12 and here it will be 24. And then this will be 2, 1 and 1. So total number of slip systems would be 6 into 2 for the first case, 12, then 24. So totally it has 48 number of slip systems. You can see that BCC has way more slip systems than FCC. Similarly, if I want to see HCP, this also has 3 different slip planes, 0, 0, 0, 1, then 1, 0, minus 1, 0, and finally 1, 0, 1, 1. We'll put 1, 0, 1 bar 1. Okay. And all of them have the same slip direction. You will see that slip direction does not change. Okay, it's just family of slip direction that will change. So, but slip direction, like the family will not change essentially, but just the individual direction will change sometimes. So essentially, you can see that slip direction is always fixed. It's the slip plane that changes every time for BCC and HCP. While for FCC, you have one slip plane and one slip direction. So this will be 1 number of non-parallel planes. This will have 3 and this will have 6. So this will have 3, 1 and 1 number of slip directions per plane. Essentially, you have 12 in HCP. 12 number of slip systems. So you can say that BCC has the highest number of slip systems, right? But one interesting fact that you can know, this is again not related to, not exactly related or something that will come in exam, but something that you can remember for your future. That although FCC has lesser number of slip systems, it is more easy to deform. Okay. Usually we'll say that if you have more, if something is more easy to deform, it means that the dislocation motion is very easy, right? But FCC is more easy to deform compared to BCC. Now, why is that the case? Although FCC has less number of slip systems, it is more easy to deform. Why? What could be the reason? Now, if I think about it, what did I say was influencing the Pulse-Nabarro energy? What was exactly influencing it? It was the value of A and B, right? That is the density of a plane. It is not the number of planes, slip planes that are available, but how densely they are packed. So here in FCC, the planes are more densely packed. Okay. Therefore, it is more easy to deform. Okay. So although FCC has less number of slip systems, it is more easy to deform due to density packed. Okay. So this is something that you can remember. It is not something that is going to come as in exam or something, but just for your knowledge, you can remember this. Okay. Okay, so now let's move on to the practice problem for today. Okay. The first question says, which of the following represents non-conservative motion for dislocation? So which of them represents non-conservative? Cross-slip is again conservative. It's a form of glide only, but gliding along a different plane. Double cross-slip is like just like cross-slip. Glide is anyways glide, and climb is the only one which is non-conservative. Just a second. Yeah. So the next question says the indices of two 111 planes in FCC crystal that contain screw dislocation with Burgers vector is A by 2 101 bar. So okay, so they are asking the indices of two 111 planes in FCC crystal that contain screw dislocation with Burgers vector A by 2 101 bar. So there are two ways to find this. Either you can use Thomson's tetrahedron or you can use dot product, right? Using Thomson tetrahedron, you can directly see which are the two planes, right? So one is 111 and one is 1 bar, 1 bar, right? So which option is correct? Sorry. Option D, right? Because 1 bar 1 bar is parallel to 1 bar 1. But if you want to see a much more clearer answer, or if you want to be sure if your answer is right or wrong, what you can do is you can take dot product of 101 bar. Sorry. With something x, y, z, right, should be equal to 0. The dot product should be equal to 0. So x minus z should be equal to 0. So in which cases is x minus z 0? So in the first case, first option is wrong. This is wrong. So therefore this option is not correct. Second case, this option is again wrong. Third case, this is also wrong. Right? So only option left is fourth one. That is the correct one. You can see x minus z will be 0 for that case. In both the options. Okay? Okay, next question. Below figure shows a transformation from state A to B. Which of the following statements are true? So they are given us some statements regarding this kind of transformation. Now we have seen what kind of transformation this is already, right? We have discussed this. This is climbing up, right? So edge dislocation is climbing up by vacancy diffusion is the right option, right? And when climbing up happens, what happens? Second option is wrong. It is not climbing down. Edge dislocation acts as vacancy sink or vacancy source. It will act as vacancy sink, right? So third option is correct. Okay. Fourth question. The motion of screw dislocation in BCC crystal is often termed as pencil glide because of the glide along A by 2 110 in 111 plane, the glide along A by 2 111 in 110, 112 and 123 plane, glide along A by 2 110 in 111 plane along with A by 2 111 in 110 plane, or the glide along A by 2 110 in 11 plane and A by 2 110 in 1110 plane. So which is the right option? Now for BCC, we have already seen, I have given you the table, right? It's the glide along 111 in 110, 112 and 123 plane. That is the right answer. The glide happens along these three directions. But why do we call it pencil glide? Now I didn't discuss that. Why do we call this pencil glide? Because the glide will happen in a zigzag fashion. Okay, the glide will not be straight. It will happen like this, like this, like this, like this, like this, like this. So the glide happens in a very zigzag fashion. That's why it's termed as pencil glide. Okay, because the planes, as you can see, even though the direction is not changing, the planes keep moving from 110 to 112. Sorry, just give me a second. Sorry, I dropped my pen. Yeah. So yeah, like I was saying, the glide keeps happening in a very zigzag fashion because the planes are all in different directions. So it will keep moving from one plane to another. It will keep jumping. So therefore, the glide will be very zigzag fashion. So that's why it's called pencil glide. Okay. So next question: the formation of the jog, does it increase the energy of the dislocation, decrease the energy of the dislocation? First option. It will definitely increase the energy of the dislocations, right? Because it is moving it out of the plane. So it will increase the energy of the dislocation, but it has to happen because there is some barrier. Okay, so it will increase the energy of the dislocation, but this is a necessary increase because something is blocking the dislocation motion. So does it aid the climb process or aid the glide process? Now we already saw that kink aids the glide process, but jog aids the climb process. So option C is correct. Next question. Match the column. So they have given us some options. We have to match and see which are the correct ones. Slip plane, Burgers vector, screw dislocation, kink, and jog formed by edge dislocation. These are the options. So for slip plane, which is the correct option? Slip plane is the densest plane, right? That is the only option which is correct. So we can say this is one. Then Burgers vector. Burgers vector is what? It is always along the closed pack direction. So this is 2. Right. Now screw dislocation. It will cross slip. So this is the option. Kink has only edge character or mixed edge and screw character. It has mixed character, right? While jog has only edge character. So you can see which one is the correct one which matches all of them. 1 to 3, okay, either first or last one. 2 to 2, 3 to, okay, 3 and 4 are interchanged. Sorry, 3 and 5 are interchanged. So this one is the correct one. 5 to 4, this one. Okay, I hope it's clear. So next question. The planar density for 110 plane in FCC crystal with edge length A. So they are asking us to calculate planar density. We have already seen how to calculate planar density, what is the formula. So let's just apply that here, okay. So first let's draw an FCC crystal. How will an FCC crystal look like? So this is how an FCC will look like, right? Let's say I'll just draw this. Okay. Now which is the plane? 110 plane, right? So this, let me use a different pen, different color. Yeah. So this is the plane, right? Oh wait, I have not drawn all the atoms. So there's an atom at each face center. All these atoms at the face center. Okay. So what is happening? Number of atoms in this 110 plane. So there's one atom at the top and one atom at the bottom face also, right? So which are the atoms which are involved? This atom, let's say this is 1, this 2, this 3, this 4, and then this face centered atoms at the top and bottom, 5 and 6. These are the atoms which are involved. So planar density will calculate the number of atoms divided by the area of plane, right? So first let's calculate the number of atoms. So we have corner atoms is equal to 4 and face centered atoms so essentially what is happening is 1/4 of every corner atom is present while half of every face centered atom is present, right? So we can write total number of atoms. To be equal to 4 into 1 by 4 plus 2 into 1 by 2. So contribution of each corner atom is 1 by 4. Contribution of each face centered atom is half. So we can do it this way and then we'll get total number of atoms to be 2. Right? Now area of this plane. Let's say this is area like each side is A for this face centered. All are A. All edges are A. So the area would be equal to 110 plane this is like a rectangle, right? So rectangles that width into height, right? So width into height if you want to do, width is root 2 times A while height is A. So this is equal to root 2 A square. Okay. So planar density will be equal to number of atoms in the plane divided by area of the plane. So that is equal to 2 divided by root 2 A square or root 2 divided by A square. Okay. So which option is correct? B. Okay. Next question. Which of the following represents possible slip system for BCC crystal? Let's just move it now. Possible slip system for any BCC crystal. So, if you want to find a slip system for any BCC crystal, what do we have to do? We just have to do dot product, right? As I have talked about, the slip plane and slip direction should be 0, right? So if slip plane and slip direction dot product is 0, then that is one condition that it should satisfy. So here we can see slip plane and slip direction for each case. If I calculate, this will be 1 for A, it will be 1 bar 1 dotted with 1 1 0. So this will be equal to 1 minus 1, which is equal to 0. So like that, if I keep going for each case, 1 1 2 1 1 1. So this will be 1 plus 1 minus 2, which will also be 0. C will be minus 1 plus 0 plus 1. So this will also be 0. D will be 0 plus 0 plus 0. So that will also be 0. So all the 4 cases are 0. So at least they're satisfying the first criteria that the slip plane and direction should be perpendicular. The dot product is 0. So now we have to check if it is the closely packed plane, the second condition, whether it is the closely packed plane. Now how do we check for closely packed plane? So we have to check for BCC crystal which are the closely packed planes. Closely packed plane and closely packed direction. So we know that 110 is not a closely packed direction, right? So it has to be option B or C. So among the B or C, which among these have closely packed planes? Let's check that out. For BCC, as we have already seen in this table, we have 110 and 112 as the two closely packed planes, and 111 as the closely packed direction. So in option B, we have a version of that. We have 112 bar, which is a closely packed plane, and 111, which is a closely packed direction. So B is correct. While in C, we have 101, which is again a correct option because we have 110 as one of the closely packed planes. So 101 belongs to that family only, and 111 family is 1 bar 1 1. So again, that option is also correct. So it's not. So there are two things you have to always check for. Okay, let me just write it down so that you can remember. First thing you have to check for always is just a minute. Yeah, the first thing you have to check for is the dot product of normal to the slip plane and slip direction should be 0. Dot product of normal to the slip plane and slip direction is 0. That is the first thing you have to check. Then the second thing you have to check is it should be a close packed plane and direction. Should be a close packed plane and direction. So what do we mean by close packed plane and direction? As I've explained before, the most densely packed plane and direction. Okay. So these two things you have to check to finally get your answer. Okay. So moving on to the next question. Just a second. Yeah. So let's move this little bit up. Yeah. So they have shown the variation of displacement del u across a dislocation in the slip plane as a function of x. It can be concluded here that B, what can be concluded? Whether width of dislocation in A is higher than that of B, or whether it is lower in A than that of B. So width is lower in A than that of B, right? So that can be directly seen. And then dislocation movement is easier in B than in A. So we have already discussed based on width. Wherever width is larger, the dislocation movement will be easier. So this option is correct. Option D is exact opposite of option C, so that is incorrect. Okay. Let me just move this. Okay. So coming to the last question for today, the factors that don't affect Piles-Nabarro stress. Is it periodicity of atoms, dislocation width, crystal structure, or the applied stress? What are the factors that don't affect the Piles-Nabarro stress? Now, if you remember, what is the formula for Piles-Nabarro stress? Let me just, I'll just write it down here. tau piles Nabarro will be equal to 2g times, okay, 2g divided by 1 minus mu times exponential of minus 2 pi w by b. Okay. So what are the things that can affect the Piles-Nabarro stress? Think about it. Does periodicity of atoms affect the Piles-Nabarro stress? What do we mean by periodicity of atoms? Periodicity of atom just means interplanar spacing, right? Periodicity, the length with which the atom repeats itself. So that's just the interplanar spacing, right? How much spacing is present between two atoms of same type. That is interplanar spacing. So periodicity just means the same thing, right? What is the spacing between two atoms by which the same atom will repeat itself? So this is wrong. It affects Piles-Nabarro stress. So we cannot say that. So periodicity of atom or A affects the Piles-Nabarro stress. Dislocation width. Now dislocation width is W, which is again there in the formula. You can see that this option is also wrong. Next, crystal structure. Does crystal structure affect the Piles-Nabarro stress? Yes. How? How will the crystal structure affect the Piles-Nabarro stress? Crystal structure will influence the Burgers vector or slip vector, right? If the crystal structure is different, the slip vector will change or the Burgers vector will change. So that will indirectly affect the Piles-Nabarro stress. So you cannot say crystal structure is directly affecting Piles-Nabarro stress, but it is influencing the Burgers vector, which in turn influences the Piles-Nabarro stress. But is there an applied stress? Is there a term which involves applied stress in Piles-Nabarro stress? No, right? Because Piles-Nabarro stress is a property of the material itself, of the crystal structure itself. It is not a property that is influenced by a stress that is applied, a load that is applied. So essentially, applied stress will not affect the Piles-Nabarro stress. So this option is right. So that is the only option which is correct. So let me just erase this. Okay. So I hope we have understood all the concepts that we have discussed here today. There are no doubts with respect to any of the concepts. In any case, if there are any doubts and any questions that you have, we can cover that in the next session. You can ask your doubt, you can post it, you can let me know. We can just have that discussion in the next session. With that, we will end today's session. I hope you have all understood how dislocation motion happens, what are the various factors that affect the slip, what are the various factors that influences the slip, what are the factors that resist the motion or glide in dislocation, what are the things that happens when this resistance comes, things like climb, cross slip, etc. And finally, how do you determine which plane and which direction the slip can happen? So we understood about how closely packed planes, etc., will influence the slip plane and slip direction in any system. Okay. So with that, we'll come to an end for today's class. Thank you for attending, and we'll meet again next week at the same time. So let's end today's session.